Welcome, everybody. So we're happy to have Joe Boninger, who will tell us about a quantum invariant of links in T2 cross I with volume conjecture behavior.
Thank you. And thank you for inviting me. It's really exciting to be here. So I'm Joe Boninger. I'm a third-year graduate student at the Graduate Center, and I'm going to be talking about quantum invariant of links in T2 cross I with volume conjecture behavior, which is right now a preprint on the archive. So this is the volume conjecture, originally posited by Kashaev in 1997 and then kind of generalized by Murakami in 2001, which says that for a hyperbolic link in the 3-sphere, Jn being the colored Jones polynomial, the asymptotic growth rate, essentially it says that the asymptotic growth rate of this invariant at this root of unity, e to the 2 pi I over n, if we appropriately normalize, then that encodes the hyperbolic volume of the complement of the link. So I won't go into too much detail about the geometric aspect, but I will talk more about the color-Jones polynomial and what this means. And feel free to just interrupt me if there's any questions. I'm not looking at the chat, but maybe somebody else can say if there's something.
I'll look at the chat. Great.
Okay, thank you. So this is the original volume conjecture, but now there are analogous conjectures which really look just like this that exist in many other settings dealing with quantum invariants of links and 3 manifolds. So it makes sense to say that an invariant, a quantum invariant that has this kind of behavior displays volume conjecture behavior. And today I'm going to define a new invariant called the nth toroidal colored Jones polynomial, which is an invariant of links in the thickened torus T2 cross I. And my main motivation for being interested in this invariant is that it has volume conjecture behavior. So I conjecture that for any link in the thickened torus, such that the complement of that link is hyperbolic, we should see exactly the same kind of volume conjecture behavior that we saw with the original color-Jones polynomial and with many other quantum invariants. And I should point out that this original volume conjecture has been verified in many cases. So we are able to prove this in many cases, but the general case still seems maybe far from a proof. And this is a very active area of research for these other conjectures. So I was able to prove this for one link, which is the 2x2 square weave here. And this is a toroidal, this is a torus. So we're identifying this side and this side, and we're identifying this side and this side. So this is a thickened torus. So I was able to prove that this limit actually does exactly reach that volume, which happens to be 4 V-oct, where V-oct is the volume of the regular ideal hyperbolic octahedron, which we see a picture of right here. So that's the volume of the complement of this weave. And approximately 3.6, but it's not so important. Beyond that, we have some computational evidence for this conjecture. So this table shows different links, which have their pictures here. And once again, these are torus diagrams. So we're identifying opposite sides. And then in the middle, we can see the relevant value of the toroidal colored Jones polynomial, and we can see the volume on the far side. And you can see that there is some kind of convergence. It seems to be quite slow, which is actually what we expect for the regular colored Jones polynomial. But you can see there definitely appears to be something going on here. So now I'd like to give a bit of background kind of leading up to what actually the colored Jones polynomial is. And it really is intimately connected with representation theory. So the beginning is we start with a quasi-triangular Hopf algebra A. So a Hopf algebra with an R matrix that satisfies the Yang-Baxter equation when it acts on modules. And I'm happy to go into more details if there are any questions. And we let U, V, and W be modules of this Hopf algebra. Now we're actually going to do a bit better than a link invariant. We're actually going to define an invariant of tangles. So a tangle is, it's exactly this picture. So it's some combination of intervals and circles that have been embedded in the unit cube, such that their boundary points are in the top and the bottom. So here we see a tangle with this one interval, two interval, and then an embedding of a circle. So note that if this didn't have any boundary points, then it would be a link. It would be an embedding of copies of S1 into three-dimensional space. So if we can get an invariant of tangles, then we can automatically get an invariant of links. So you'll notice a few more things about this diagram. So it's not just tangles. We got to be a little bit more specific. Well, number one, these are oriented tangles. You can see that they have orientations, and they're actually framed. So I've drawn them without the framing, but that just means that the framing is in the plane of the diagram. So we just think of that as a thickening in the plane of the diagram. So they're actually bands. And that just limits the kinds of things that we can do with them, which makes it a bit easier to get an invariant. So this is in fact an invariant of oriented and framed tangles, and we need one more thing. So you'll notice that these tangles, each component has been colored with one of our A modules. So we call that a colored tangle if each component is labeled with an A module. So the goal is to produce an invariant of oriented, framed, colored tangles in the unit cube. And we're going to do that by constructing a functor which associates this tangle to an A linear map, and each top and bottom boundary component of this tangle with an A module. So here, the top boundary component is associated to the module V tensor W tensor the dual of W. Here it's the dual because the arrow is pointing up and this arrow is pointing down. So that's just W. And that's why we need a Hopf algebra, so we can get that. This is still an A module, right? And the bottom gets associated to V because we just have V there. So that's how we get these boundary A modules. And the tangle itself, our functor is going to send this tangle to this A linear map FT from V to V tensor W tensor the dual of W. So that's the goal, is to create this functor. And from that functor, we're going to get the Color-Jones polynomial. So when I say functor, it's actually, it's a monoidal functor. It has some nice properties. So if we can decompose these tangles into these horizontal and vertical juxtapositions. So if we have two tangles, we can juxtapose them horizontally, like so, here on the top and bottom. And we think of that as the tensor product. And we can also juxtapose them vertically if we can get the boundary components to line up. And we think of that as composition. So our functors actually needs to behave nicely under these two operations. So here, this tangle T gets associated to F of T, but because we can decompose T into this T1 tensor T2 composed with T3 tensor T4, or actually going the other way, T3 tensor T4 composed with T1 tensor T2, that means we can decompose the A linear map into FT3 tensor FT4 composed with FT1 tensor FT2. And this is very nice for obvious reasons, but also because what this means is if we want to assign our A linear map to T, actually all we have to do is assign A linear maps to these smaller tangles. And then the more general map will follow immediately from this composition property. So that's how we build this functor. We actually just worry about these little elementary tangles. So we have a crossing, and we could also have a negative crossing, and these are all oriented. And we have a cap here, and we could also have a cup like that. So for example, this is the identity map from some module to itself. This is the R matrix, which is why it has to be a quasi-triangular Hopf algebra. And if we have, for example, a cup that's oriented, I have to remember how it's oriented, like this, I think, then this is a map from V dual tensor V to nothing, which is the ground ring, which is C. So this is a map from V dual tensor V to C. This is the evaluation map. So very natural.
Sorry, can I ask a
Yeah.
question? Could you just briefly say in why is this decomposing this tangle? Just, topologically what's going on.
Yeah, topologically, we're really just sitting the blocks next to each other, right? So we're just going like.
Yeah, so how should I look at this picture? Yeah, okay, thanks.
Actually, I did that wrong. Hold on. It would be like that. So that's the decomposition. All right. So this block is just this.
Right.
Does that answer the question?
Yeah, yes, absolutely. Thanks.
Cool. Yeah, thank you. Yeah, so it's a bit more complicated when we get to, there's a few other maps we need to throw in there, but generally this is the idea behind this construction. And if we had a negative crossing, this is actually our inverse, right? And the really cool thing is that because of this choice of maps, this is actually an isotopy invariant. So if we have two tangle diagrams and we can move the tangle around in 3 space to make one look like the other, that means they're associated to the same alinear map. So that's really the cool thing about this construction, which makes it produce invariants, which makes it work. And once again, like the R matrices are this kind of the secret ingredient there, satisfying the Yang-Baxter equation. So, okay, having done that, we can now say what the color-Jones polynomial is. So we specialize to the quantized universal enveloping algebra of SL2C, which has one irreducible representation in each dimension. So we let V be the n-dimensional representation. So given a knot or a link, like this is the trefoil, for example, we can always kind of snip it in one place, and we can turn it into a 1-1 tangle like this. So now in our theory of operator invariance, which we just came up with, that's going to associate this tangle to an alinear map from V to V. However, because this is an irreducible representation, by Shor's lemma, this map is actually just a scalar multiple of the identity. And it's a scalar given in terms of our Q, whatever we are, fixing in our what we're quantizing to, right? So this map is a scalar in terms of Q. This is you could think of it as C adjoin Q, or we can just let Q be like a root of unity, Q plus or minus 1. It's a Laurent polynomial in Q. Yeah. So this map is a scalar times the identity, and that scalar is the color-Jones polynomial. So this is one way to define the color-Jones polynomial of a link. And you'll notice there's some kind of normalization factor out in front here, which is WD is the writhe. So we kind of just sum the signs of the crossing, but that's not so important, especially not for our purposes. It's essentially just whatever the scalar defining this map is. And because there's one irreducible representation, then we get one color-Jones polynomial for each n. So it's actually an infinite family of polynomials. So this is probably the original construction of the color-Jones polynomial, which I want to say is Reshetikhin and Turayev. I won't write their names right now. But yeah, there's a lot of people have worked on this theory. It's very well developed. So, okay. Last thing about the color-Jones polynomial, we've defined it. How do we actually compute it? So once again, we use our decomposition, right? So we look at this crossing. So, we decompose this into elementary tangles, crossings, caps, cups, just vertical strands. And we have our R matrix, which is a map from V tensor V to itself in this context. And we need this other map mu for certain caps and cups, depending on how they're oriented. But it's just an alinear map from V to V. So to compute this scalar, we can fix a basis element on the top and bottom, and then we can just actually compute it using the definition of R and mu, right? So they're defined in terms of these scalars in C if we fix a certain basis, and then we can compute it as a state sum over these basis elements. So, each strand we think of here as getting a basis element of V, and then we can just compute it in terms of these coefficients. So let me know if that doesn't make sense. And this is kind of called the state sum construction, where we think of these basis elements as states of the diagram, and then we sum over the defining coefficients of these maps in that basis. So this is how you compute the Color-Jones polynomial. Okay, so having done this, now I'd like to define my toroidal Color-Jones polynomial. So this is now a link in a torus. It's actually a knot, and this is actually the virtual trefoil, I believe is what it's called. So you'll notice that we can't necessarily, well, there doesn't seem to be a natural way to associate this to an alinear map. And the issue is that it wraps around here. So we can't just read from top to bottom and compose things because it skips around to the other side at this point. So that we can't really do that whole operator invariant construction. However, the state sum construction is completely valid. So we can still say, well, locally, we can decompose this into our elementary tangles. So we can still say, okay, well, a crossing is an R matrix, and a cap oriented one way is the evaluation map, and a cap oriented the other way, we have to add in this little operator mu. And then we can actually just do the same thing that we did on the previous slide and take a state sum. So essentially, locally, we have alinear operators, but globally, there's no alinear operator here. So I've called this a pseudo operator invariant. And the same construction will work for any quasi-triangular Hopf algebra. But if we specialize, once again, to the quantized universal enveloping algebra of SL2C, then we get the toroidal Color-Jones polynomial.
Do you need to restrict to knots, or does this work for links as well?
Yeah, this is totally general. It works for links. It works for, yeah, knots or links in the torus. Yeah, and once again, we have this same normalization factor out here, but that's not so important to the theory. So just to be a little bit more, rigorous about how we're defining this, because a priori, this could depend on our choice of diagram, and it could also depend on our choice of basis. So what we're really doing is we're exploiting the flat geometry of the torus. So if we have a link in a torus, we can lift it to the universal cover, R2, and then it makes sense to assign local maxima and minima if we're looking at a diagram in R2. So a priori, this could also depend on the choice of covering map that we pick to do this lift. But it turns out that it doesn't. And I might talk a little bit more about that. Now I'll say one more thing about this. So there's no way to get an alinear operator out of this, as I mentioned. We can still get some sort of operator out of it. We can still get a C-linear operator out of it if we do this. So I can draw a little curve going across here. Maybe I should make it slanted, but it's hard to do because I made the diagram vertical. So it was, something. Okay, I'm going to try one more time. Like that, and then we can kind of ignore this part. Right, and now we actually can read this from top to bottom if we just connect the part where it wraps around. And where we see, it crossing itself here, we think of this as like we want to kind of ignore this crossing. So instead of giving this the R matrix, we would give this just the map tau, like the transposition map that sends A tensor B to B tensor A. And same thing here and same thing here. So if we just draw that line going across the diagram, now we actually do have a map that we can read from the bottom to the top. If we just let these these virtual crossings just be this swapping map, and that kind of helps us ignore them. The issue with that is, and this is actually how you prove basis invariance. So this construction is how you prove that it doesn't depend on the basis. However, the issue here is that this swapping map is not generally alinear. So we still have a linear operator, but we don't have an alinear operator. So still a pseudo operator invariant. So some properties of the toroidal colored Jones polynomial. Well, it's unchanged by homeomorphisms of the torus. So on the left here, we have a link in a torus, and it's a very simple link. It's just a longitude. And here, this is a homeomorphism where we just twist it around. So because these links are related by a homeomorphism, the toroidal colored Jones polynomial will take the same value on both links, which is an interesting property, partially because the Jones polynomial does not satisfy this property. So if we have a link in the thickened torus, its complement is actually homeomorphic to a complement of a link in the three sphere. So we can actually think of this as a link in the three sphere if we just add two components here and here, representing the removed cores of the tori, right? So this link is a link in S3, which has the same complement as this link in the torus, because we've just added these two components that kind of capture where the torus is cutting out. So these two links are two links in S3. Yeah, if anybody wants me to say more about that, I can. So these are two links in the thickened torus. These are two links in S3 whose complements are who are also related by a homeomorphism, right? That just twists this around here. But the colored Jones polynomial will not take the same value on these two links, whereas the toroidal colored Jones polynomial will take the same value on these two links.
Joe, in that top picture, so that's an unknot in the torus.
It depends on your definition of unknot, right? It's not contractible, but it's certainly not like crossing itself.
Okay.
It's a longitude. It's kind of an unknot.
Yeah, that's what I wanted to ask. So what is the, do you know off the top of your head what the invariant is assigned to that picture?
That's actually the next bullet point. So great question. Yeah. I'm saying that in a sec, but so this is an interesting property that suggests that this toroidal colored Jones polynomial really is capable of capturing some things in a different way than our colored Jones polynomial is, right? It's maybe a little bit more geometric in that sense, even though it's less sensitive to these homeomorphisms. And this is actually how you prove that it doesn't depend on the choice of covering map in the previous slide. You just prove invariance under these twisting maps, which is not so hard. Because it turns that's kind of all of the important homeomorphisms of the torus that we need here. So yeah, so the second property, just like Josh was asking about, so these are, once again, we're going back to our flat torus picture. So this is a torus diagram. So for an essential simple closed curve like this, which we could think of as the same curve as that longitude in the previous picture, it's actually the nth toroidal Jones polynomial is just n. And this is actually quite easy to see because this is the identity map. So it's really the trace of the identity map in n dimensions, just the regular trace, not any kind of quantum trace. So it's just n. Yeah. And then if we have a contractible simple closed curve, and this is the same for the regular colored Jones polynomial, that value is kind of a quantum trace. That's the quantum integer n, which is defined by this quantity in terms of q. So this is a very interesting property for me, right? It kind of quantizes these contractible curves, but it doesn't do that to these essential curves.
I'm sorry, Joe, could you explain 2 again? I was half paying attention to that.
Yeah, so the value is n, which we can think of, if it doesn't wrap around at all, then you can just think of this as like a regular alinear map.
Yeah.
So the map here is the identity. So this is really the trace of the identity map.
But you're not taking the quantum trace there.
No, because it's just going from top to bottom, right? So what was our definition was a state sum, right? So it's really just the sum from I equals 1 to n of 1, because all the defining coefficients are, so it's just n.
Okay.
Yeah, it's not a, it's just a regular trace because there's no like cups or caps in the diagram.
Okay.
This diagram does have these cups and caps. So this diagram is the quantum trace.
Okay. Thanks.
Yeah, I think there's like multiple concepts of quantum trace, right? But this is one of them.
Okay, thank you.
Yeah. So this is really a generalization of the colored Jones polynomial, right? Because you see this happening with the regular colored Jones polynomial, but you don't see this because there are no curves like this in the three sphere. There's no essential curves, right? So this is an interesting property that we have n for essential curves and quantum n for contractible curves, which I can talk a bit more about maybe at the end if we have questions about it. But I've thought about, I definitely cannot totally explain why this happens, but I have a bit of some justification for it. So a few properties of the toroidal colored Jones polynomial. And another very interesting property. So we made this volume conjecture earlier. It turns out that if you generalize this volume conjecture to simplicial volume, which I won't talk about, just a slight generalization of it from the hyperbolic case, it actually implies the original volume conjecture. So in this sense, our volume conjecture actually, even though it seems to be about just things in a torus, it actually generalizes the original volume conjecture. And the proof of this is actually quite short. So if we have a link in a three sphere, which we can represent by T, if you'll recall our definition of the colored Jones polynomial, we just cut it and we represent it as a 1-1 tangle. But diagrammatically, this 1-1 tangle it's the same thing as if we took a torus diagram, if we took a link like this in a torus. So this is a torus diagram. This is a 1-1 tangle, but when we compute them, it's basically the same computation. It's just a state sum. The only difference is when we compute this, right, it's the defining scalar, so we don't sum over the top and bottom basis element. We kind of fixed that. And here we have to sum over everything. So we get this extra factor of n. But essentially the computation is the same. And I should point out that the diagram is the same. These are two different links. So this link is the link T wrapped around the torus. This link is a 1-1 tangle representation of something in a three sphere, right? So these links are different links in different places, and they don't have the same complement. They just happen to have the same diagram, but it turns out that their complements have the same volume. It's not the same, it's not a homeomorphic complement, but the complements have the same volume. So for that reason, if we prove the volume conjecture for this, then we automatically prove the volume conjecture for this, which is interesting to me. So, the construction can seem a little bit artificial, but I think these properties argue that actually this is a very natural construction that is maybe even generalizing the original construction. And now I'll give a bit of a sketch of how I proved this theorem, which once again, I was able to prove the volume conjecture rigorously for this one link, which is the 2x2 square weave. And here's just a reminder of what it actually says. So we're looking at the asymptotic growth rate at this root of unity as n goes to infinity. So the key ingredient is the result by Garofalidis and Ley from 2011, which is looking at the defining coefficients of these R matrices in our preferred basis. So the result is essentially that if we take any one of these defining coefficients and we evaluate it at the relevant root of unity and we take the relevant limit, then it's actually bounded above by this volume of the regular ideal hyperbolic octahedron, which we saw that picture of in a previous slide. So this is an interesting theorem all on its own. And there's a little bit of motivation for thinking about this, which is, if you'll recall, in our construction, every crossing gets an R matrix. Well, there's also a geometric construction where we can give a link complement a hyperbolic structure by assigning one octahedron to every crossing, as we like this picture shows. So it makes sense that if we believe the volume conjecture is true, then we might expect there to be some relationship between R matrices, which are an algebraic thing assigned to a crossing, and octahedron, which are a geometric thing that we can assign to a crossing. And the regular ideal hyperbolic octahedron is the one that maximizes volume out of all hyperbolic ideal octahedron. So that would be the one that we would expect to be the upper bound here. And that turns out to be true. The proof is very analytic, I should say. It really is, just uses the nitty-gritty details of the definitions. So it's not too hard having this to prove that this limit is bounded above by the volume of the regular ideal octahedron times the number of crossings. Since we're assigning one R matrix per crossing, and this is really the operator that matters in the limit if we're just thinking about an upper bound, right? So we have this bound following from this result, that this limit is bounded above by V oct times the number of crossings. And for the case of the 2x2 square weave, and this has been kind of explained by Ilya Kaufman, who's here, and Abhijit Champanarkar and Jessica Purcell in one of their papers. For the 2x2 square weave, the complement, actually the volume is exactly this 4V oct. We can actually assign a regular ideal hyperbolic octahedron to every crossing and get a structure that way. So automatically, just from these few results, we have that the limit is bounded above by the thing that we want to prove that it converges to. And this is another special thing about tori, where you think it's a bit weird to be working in a torus, but this actually doesn't happen in the 3 sphere. This is a kind of a torus specific thing where we can hit this bound exactly. So you still have the bound in the 3 sphere, but this is this family of links, right? So we can make bigger square weaves. But this family of links is really kind of the only example that I'm aware of where this bound is actually hit exactly. So it's a very natural family to study for this conjecture. So since we have that bound, it suffices to show the lower bound. I'm not going to go into a lot of details, but I'll go into just kind of a quick sketch. So, first we want to compute an explicit formula. So the proof is very nitty gritty again. So we assign our basis elements to strands, and in fact the coefficient of the R matrix is actually also a summation in terms of this M. So you end up with a multi-valued sum like this in terms of R matrix coefficient, and when you expand it, you do a little bit of manipulation. So there is some work here, but you get this formula where these are quantum integers, and I don't know what we can get out of it, but there's a lot of symmetry. It's kind of a beautiful formula with some interesting properties all on its own, not even thinking about volume conjecture behavior. So the first step is to write down this formula, do a little bit of manipulation to it, and if we do a bit more manipulation, we can write it as another sum which is all positive and real, which is also odd because typically for most links, these terms, these summands are complex and they're very much not positive, and it's very difficult to show convergence. But if we do work and we manipulate this, we can actually come up with a sum of non-negative real numbers. And then we can show that sum is bounded below by this one specific summand, which converges to exactly what we need it to converge to. So a very quick sketch of how we proved this theorem.
I make a quick geometric comment.
Yes.
There exist octahedral links, so links whose volume is an integer number of regular ideal octahedra. What makes this family very special is it's one octahedron per crossing. So
Thank you. Thank you. That's a good comment. There are also tetrahedral links where it's ideal hyperbolic tetrahedra. And there's toroidal links that have that property as well, but I was not able to prove the volume conjecture for this.
and that kind of behavior, that one octahedron per crossing, is impossible in the three-sphere. It has to be in the thickened torus.
Yeah. Thank you. Thank you. Okay, so that was kind of, you know, the volume conjecture component of the talk. Since I have a bit more time, I'll discuss a different perspective for this invariant. If you're familiar with the Color-Jones polynomial or the Jones polynomial at all, you know that there's also this Skein theoretic perspective. So if this is going to be a true analogy to the Color-Jones polynomial, we should expect an analogous Skein theoretic perspective. And it turns out that there is one if we define a bracket like this recursively. So this is a diagrammatic bracket where if we have a closed curve that's disjoint from our diagram, we can remove it at the cost of multiplying by this factor. So the bracket is in terms of two variables, A and Z. And so this is for a contractible curve. If we have an essential curve, we can remove it by multiplying by our second variable, Z. And finally, if we have a crossing, we can resolve it these two ways, which are related by these coefficients. So if you're familiar with the Kaufman bracket, you know it's just these two, the top and bottom things, right? But we don't have any non-contractible curves, so we wouldn't have a second thing in the regular Kaufman bracket. You know, and of course,
should I be thinking of A as the Q or some relationship?
yes. So we're going to normalize A and get Q out of it.
Okay. And should I be thinking of Z as some number actually?
Yes, that's exactly right. Yeah, good question. So Z is, so the exact relationship I think is A to the fourth is Q, and for our purposes, Z is just going to be 2. Like we talked about how it's very simple on essential curves. So here's an example computation. This is a longitude with a twist in it, or maybe a meridian with a twist in it. So using this number 3, we can resolve this crossing in 2 ways. Now this we can remove from our diagram using number 1, and that gets us our negative a squared minus a to the negative 2. And this we can remove from our diagram using 2. So that gets us our Z. Now here we just have one essential curve, so that is just a Z. So I'm happy to go into a bit more details, but that's an example of how you compute this. So it's kind of clear that we can compute it. We just remove crossings until we have circles, and then we take out the circles. So the value of this bracket on this meridian with a twist in it is negative a to the negative 3z. And there is also representation theory here coming from the Temperley-Lieb algebra, which I won't say anything about, but maybe you might be familiar with it. So the result here is that if we normalize this appropriately, and now you can actually see where this normalization, why we actually need this, because we had this factor in that calculation we just did, and we need to get rid of that factor because we want this to just be Z, but this negative a to the negative 3 comes from this twist here. So we kind of have to do this normalization, which you have to do in the regular Kaufman bracket as well. So the theorem is that if we take our bracket, we normalize it in exactly the same way that we normalized before, and then we specialize a to the 4th equals q and z equals 2. That's actually our level 2 toroidal colored Jones polynomial, which we could think of as just the Jones polynomial, but in a torus.
For a link, could you just have multiple values of z where it takes on natural numbers?
Yeah, I mean, there's nothing wrong with letting z be a variable, and I should say, all the examples we've looked at, we colored if we're talking about a link, then we've colored every link component with the same A module, right? But this construction actually works if we color different link components with different A modules. So you can actually make this more general, and then you could talk about not just JN, but you could talk about like JN1 and 2, where you pick a different color for each link component. So that's kind of analogous to what's happening here in the Skein theoretic perspective. But there's nothing wrong. Like this would still be an invariant leaving z as a variable. The only reason that we're specializing to 2 here is to get it to agree with our other definition in terms of pseudo operator invariance. And I should say this is a different quantum group. And this is also completely analogous to the usual case. If we're talking about operator invariance, we're talking about UQSL2C. If we want to do Skein theory, we're actually talking about SU2, or actually SU2Q, the quantization of that. But we just call it SU2 in the theory. So it's not exactly the same as the other construction. It's a different quantum group, but that's completely analogous to the Color-Jones polynomial, and they're closely related, right? They're kind of different normalizations. Yeah. So this is the last result, which is that this invariant we can define also from another perspective, completely Skein theoretically, just like we can define the regular Color-Jones polynomial completely Skein theoretically. So this is just level 2, but we can get all of the levels using this cabling formula. So it's complicated, but the point is that in fact the higher levels can be expressed in terms of this bracket. This is really like the level 2, right? So the higher levels can be expressed in terms of the level 2 invariant, in terms of this bracket. If we think about cabling our diagram, so this is n minus 1 minus 2j cables, where we have the pictorial. So this is a 2 cabling, right? And this is a 3. So this is what it means to cable, right? So in fact, the invariant at all levels can be expressed in terms of cables of the diagram and just the level 2 invariant. So even though this bracket only is equal to the level 2 invariant, we can actually recover all of the invariants, which is the same as in the usual theory. And the reason why we can do this is because of the representation ring equality in SU2Q, which expresses these the n-dimensional irreducible representations in terms of the 2-dimensional irreducible representation, where this is a tensor product here. So it turns out that taking a tensor product is kind of like cabling the diagram, actually. And this same equality actually holds in the representation ring of UQSL2C. So we actually also have a cabling formula in that case. But this is the cabling formula that we need to get our Skein theoretic toroidal Color-Jones polynomial. And there's, I don't know if anyone is familiar with the Kaufman bracket Skein module, but we can also think of this as a specialization of the Kaufman bracket Skein module, where essentially, right, so basis elements of that are kind of the essential curves. So if we just send every basis element to 2, then we can also think of it as in that way. And if you're familiar with that perspective, this is interesting because it's the first example that I'm aware of volume conjecture behavior coming out of some Skein module that's not the Skein module of S3. It's the Skein module of T2 cross I, which has a lot of other interesting properties independent of that. So a couple directions for further research. Question 1, how does this, right, so if we're thinking about a link invariant, we can always think about the complement. And it's natural to ask how the toroidal color-Jones polynomial of a link might relate to the Toraya-Viro invariant of the complement. So the Toraya-Viro invariant is a quantum invariant of 3 manifolds. It was discussed in a talk a few weeks ago here by Chin Tao. And it's a state sum on tetrahedra, and it's also very representation theoretic. And in the case of the usual color-Jones polynomial, there is a result that relates them. So we would expect there to be maybe an analogous result here, but I don't know what it is. So this is a good question. And if we knew this, then we might be able to use this volume conjecture to prove something about the volume conjecture associated to the Toraya-Viro invariant, which was actually, right, Chin Tao was one of the people who made that volume conjecture. So if we had a relationship, we could maybe use them to get information about each other. And second question, which some of you may have been wondering already, is, why do we have to just talk about a torus? Can we say anything about a link in a higher genus surface? So in the construction of the invariant, of the pseudo operator invariant, we actually very heavily used the fact that we were in a torus because we used the flat geometry and the fact that we can assign, local maxima and minima. We can talk about cups and caps in a consistent way. So there's not an obvious way to do this in a higher genus surface, but the Skein theoretic perspective is completely valid. So that bracket that we defined a few slides ago, there's nothing wrong with using that bracket in a higher genus surface, like a 2 genus surface. And that will still give you a link invariant. So that all the theory goes through there, just not the pseudo operator invariant theory. And we wouldn't expect to get volume conjecture behavior in the same way for a few reasons. Number one, because the notion of a hyperbolic structure on higher genus surfaces is actually a lot more ambiguous than on a torus. So we need to do a little bit more specification there. And we can come up with specific examples, right? So we know from that result of Garofolitis and Ley that it's kind of bounded above by the crossing number. And we have specific examples of higher genus surfaces where the volume is much higher than the ratio given by the crossing number. But even so, there may still be something that we can say. It may be possible that this bracket in higher genus surfaces encodes some kind of geometric information. And that might be an interesting thing to look into. So thank you. That's the talk.
Thank you. Let's thank Joe for that great talk. I'll stop the recording.